Good afternoon and welcome to today's lecture. We are going to continue our discussions on functional dependencies and how we can design databases using the concept of functional dependencies. Just to refresh our memory, we talked about this notion that this functional dependency we represent as alpha to beta, where alpha is a subset of R, where R is a relation schema, and beta also is a subset of R. And we say that alpha to beta, which we read as alpha functionally determines beta, or beta is functionally dependent on alpha. It holds on R if and only for any legal relation lowercase r defined on this schema R. Whenever in such a legal relation, whenever two tuples T1 and T2 of R agree on the attributes alpha, that means the attributes that comprise the set alpha, they also agree on the attributes beta, that is T1 alpha equal to T2 alpha will imply T1 beta equal to T2 beta, where T1 alpha means that the values of tuple T1 for the columns that are there in alpha, and likewise for beta. So this is what we had discussed, and this was some example. So now we will proceed further on the use of functional dependencies. But before I do that, is there any question? Okay, so if there is no question, I will continue. So, what is the use of functional dependencies? We can use functional dependencies to do two things. One is to test relations that are given to us to see if they are legal under a given set of FDs. That means that we are given a set of functional dependencies and we are given a relation R on capital R, and we have a set of FDs that are defined on capital R. So if a relation R is legal under a set F of FDs, we say that R satisfies F. The other is that the specified constraints on the set of legal relations. That means that we say that F holds on R if all legal relations on R satisfy the set of FDs F. That means we say that you see that this schema R, so from there if we form different relations lowercase r, then it has to, all of such legal relations will have to we have to hold, or we'll have to satisfy this set F of functional dependency. So it needs to be noted that a specific instance of a relation schema may satisfy an FD even if the FD does not hold on all legal instances. So we will not consider that particular schema to be or that particular relation on that schema to be satisfying that FD. So for example, if we have a relation where say for example, if we consider this case, so we see that we know that ID functionally determines name, but because these names are all unique, so it might appear that name also functionally determines ID. So remember that we start with the FD. So if we say that a name does not functionally determine ID, so that would mean that we can have multiple or repetition of names for same name for different IDs. Okay. But ID to name FD would mean that given a fixed value of ID, the name itself will get determined. So that is what is mentioned here, that a specific instance of a schema may satisfy an FD even if the FD does not hold on all legal instances. And this is the example that I just now mentioned. An FD is said to be trivial if it is satisfied by all instances of a relation. So we see that if we write ID comma name functionally determines ID, or name functionally determines name. So these are trivial functional dependencies, because if we fix ID and name, of course that means ID gets fixed. Or if we fix name, then on the right hand side also the name gets fixed. Okay. So in general, alpha to beta is said to be trivial if beta is a subset of alpha. So even then we treat these as functional dependencies, because this indeed holds for all legal relations defined on schema R. Okay. So we are defining this notion of trivial functional dependencies, and we will see that this notion of trivial functional dependency is actually also used while defining what are good relations. Now, given a set F of FDs, there are certain other FDs that are logically implied by F. So this is important, that we are given a set of functional dependencies F on a legal relation R. I'm sorry, on a relation schema R. Okay. So now we are saying that if we are given a set of such functional dependencies on a schema R, and we denote this set of functional dependencies by uppercase F, then there are certain other FDs that are logically implied by F. For example, if we have these two FDs, A determines B and B determines C, and now then these are two functional dependencies, say F1 and F2 in the set F of functional dependencies, then it can be inferred that A also functionally determines C. Okay. So there are a few other rules which we'll see a little later. But what is important is that this is what we mean by uh, getting new functional dependencies by through logical implications of the set of FDs given to us as capital F. Okay. Now, the set of all functional dependencies logically implied by F, that means F is given to us, which is a set of functional dependencies to start with, and then the set of all functional dependencies that are logically implied by F is called the closure of F, and we denote the closure of F by F plus. And of course, F plus is a superset of F, which is trivial. Now, in this example, and we'll see a lot of examples later, we have F is basically, say, F1 is this set having two functional dependencies, F1 and F2. Then where F1 is A to B and F2 is B to C, then F plus will be equal to this F1 F2 union, of course, the new dependency, that is A to C. So then F plus will be having these three functional dependencies in it, A to B, B to C, and A to C. And of course, it is trivial to figure out that F plus is a superset of F. Now, armed with these definitions like trivial functional dependencies and what is meant by meant by closure of a set of functional dependencies, we now formally define. If you remember, we said that there are certain normal forms which characterize the goodness of different relations or relation schema. So, relation schema R is in what is called Boyce-Codd normal form, BCNF, with respect to a set F of functional dependencies, if for all functional dependencies in F plus. So this is something that you have to understand, that R is BCNF with respect to a given set F of functional dependencies. So that means that we are given a schema R. That means we are given what are the columns of R, and we are given a set F of functional dependencies, means that we are given FDs like this, say A to B, B to C, etc. And then the definition of BCNF is with respect to all functional dependencies that are there in F plus, which is, as we said, is the closure of the set F of functional dependencies. So now, what is the definition? If for all such functional dependencies that are in F plus of the form, say, alpha to beta, where alpha is a subset of R and beta is a subset, also is a subset of R. So either alpha to beta is trivial, that is beta is a subset of alpha, or alpha is a super key of R. So if we see here that what we said is this trivial functional dependency, that alpha to beta, this FD is trivial if beta is a subset of alpha. And this definition of BCNF, it makes use of that concept of trivial functional dependency. And if it is not trivial, then for all such FDs of the form alpha to beta in F plus, alpha is a super key of R. That means alpha functionally determines R. So if you remember, we said that this concept that alpha, if it functionally determines R, so alpha becomes a super key, and which is obvious because the definition of super key is what? That a set of columns together form a super key of R. If we fix the values of those columns for any tuple, the values of all the columns for that tuple will get fixed. That means the values for all the columns in R will get determined, or that means that R itself will get determined. That means this alpha functionally determines R, okay? Or R is functionally dependent on alpha. Then we call alpha to be a super key. So the definition of BCNF is that for all such functional dependencies alpha to beta in F plus. So this BCNF is R is in BCNF with respect to a set of functional dependencies F. So remember that if you are simply given a schema R with no set of functional dependencies, there is nothing that we can say about whether R is in BCNF or not, because this concept of BCNF is with respect to a set of functional dependencies only. So then alpha to beta is trivial, or alpha is a super key of R. So example schema that is not in BCNF, if we see this, now we understand as we had started with the example. So here if you see that this is underlined just to show that, say, don't take that these are primary keys, okay? So it is only to let us focus on these cases that we have this ID, name, salary, department name, building, budget. So here we see that department name, okay, that department name functionally determines building and budget. So we are making an assumption here that this building will be fixed for a department, and a budget also will be fixed for a department. So that means that if we fix the value of department name, then we get uniquely the name of the building. Also, we get uniquely the amount of budget. So that's why we are writing the department name functionally determines building and also functionally determines budget. So we see that in this instructor department schema, however, department name is not a super key. Okay, because for the same department we can have many different values of IDs, names, and salaries, and hence department name is not a super key of this schema instr underscore department. And because it is not so, that means that a department name is not a super key of this relation schema. So we have this functional dependency department name to building budget, where department name, which is alpha here in the above definition. So this department name is not a super key, and hence this schema that is instr underscore department is not in BCNF. And that is the reason what we saw here, that we said it is not a good design because there are some repetitions and all, but these are all intuitively we are talking about. And of course that for this example it is true that we all understand this concept of department name being housed in a building and department has a budget and so on. But when you are analyzing completely or designing a database for a completely a new domain where you do not really know what is what, and especially when there are so many different such attributes and their meanings, and there are hundreds of such attributes and there are many dependencies. So as such, as a designer, we may not know what is what and what are these FDs and so on. So it is important that if we are given a schema like this instructor department with ID name, salary, department name, building, budget as its columns, and then we are given these functional dependencies that department name functionally determines building and budget. then we can immediately, now as good designers who have understood this concept of normalization, then we can figure out that this schema is not in BCNF because department name is on the left hand side of a functional dependency that is like alpha, and department name itself is not a super key. And of course this is not a trivial functional dependency because building budget, this set is not a subset of department name, and hence this is neither a trivial functional dependency nor alpha, that is department name is a super key of instr underscore dept, and hence what we have here is that we have uh, this particular schema which is not in BCNF. Now, if a schema is not in BCNF, so that means that there are indeed certain redundancies. Okay, so if it is not in BCNF, and there is a non-trivial dependency alpha to beta, which is causing a violation of BCNF. So if we had here, for example, the other FD was given, say, ID functionally determines name, salary, department name, building, budget. So where ID, of course, is a super key. So that FD definitely is not causing a violation of the BCNF property. But this FD, department name to building budget, is the one that is causing violation of the BCNF property. So what it says is that that there is a non-trivial dependency alpha to beta which is causing the violation of BCNF. Then what we'll do is that we'll decompose this schema R into two schemas. One is R1 will be alpha union beta, and R2 will be R minus beta minus alpha. So if there is any of these columns which are there in both alpha and beta, so those are removed from beta, and then that is subtracted from R. And remember that these R etc. these are all schemas, meaning these are all collections or sets having different columns, as R is a set with different columns as its elements, and similarly alpha and beta are also sets of columns. So it makes sense to carry out this set operation. So we simply decompose R into two relation schemas, R1 and R2, where R1 is alpha union beta and R2 is R minus beta minus alpha. Now in this example that we had here, so we are having this problem with department name to building budget. So alpha is department name and beta is building budget. So beta minus alpha is building budget, and alpha union beta is department name building budget. So we'll have these two schemas. One is R1, which will be alpha union beta, which means that it will have department name comma building budget, and the other will be R minus beta minus alpha. So that means that it will have ID name salary department. So of course you see that in the process what we have done is that this instr dept, which we intuitively previously knew is not a good design, there are redundancies and all these things which might cause inconsistencies, but now we have formally figured out why it is not a good design, because we now know that it is not in BCNF. So BCNF is a standard level of normalization which we try to follow in our database design. So we have this situation where we have identified that this schema is not in good form. So it is because it is not in BCNF, and we know why it is not in BCNF, because of which functional dependencies, and now we know that how then to decompose this into more than one schema, so that we expect to get rid of this violation of BCNF property. Now, as we see here, that this actually you all possibly had also intuitively knew that this is supposed to be the schema. One will be ID name, salary, department name. The other is department name, building, budget, and of course that means that we are having this department name in this other table, and if we need to get back the building and budget for any ID or name, then we can join using this department name with that department name, and we can get back the values for building and budget for any given value for ID. Okay. So that is what is meant by decomposing a schema into BCNF. But remember, and we'll see some example, it is not necessary. This first level of decomposition will always result in schemas which are in BCNF. So in this example, these are in BCNF. These two schemas that are shown at the bottom: department name, building budget, and the other is ID name, salary, department name. But we of course had one simple such FD which was getting violated, and we could actually decompose into two schemas which are then in BCNF. But always remember that when we have a large number of functional dependencies that are there in F, and we also have to consider F plus, and once we have done it, this decomposition, it is not guaranteed that each of them individually will now be in BCNF. So you have to test for the BCNF property for each of these, and if not, then the one that is not in BCNF, or both are not in BCNF, then we have to further decompose it, and we may have to keep doing it a few times at different levels till we end up getting the schemas that are all in BCNF. And why we are saying in BCNF? Because it is good to achieve, or good to target to achieve this BCNF property in our database schema. So, but there is one issue that there are these functional dependencies which are to be checked. So, what is that we mean? That if you remember that if we said that these are the functional dependencies, then anytime we try to enter any row in this table, we have to ensure that the FDs are not violated. Now, suppose we do a decomposition here, and then if there are some of these functional dependencies, and we want to check whether these FDs are violated when rows are inserted in the decomposed schemas, then if for checking the FDs we have to join them for checking it, then the cost of checking the functional dependencies from a set of decomposed schemas will be going up, because always remember that joining something is always going to be expensive. And because of that reason, um, uh, what can happen is when we are decomposing a schema which is not in BCNF to get BCNF schemas using this formula, okay, then what can happen is that the resulting schemas are such that for checking certain functional dependencies, we may have to join them to actually be able to check for them. Now, if that is the case, then this decomposition is not what we call as dependency preserving. Okay, so but the problem is that it is not always the case that as we'll see some examples where when you try to decompose it, we don't always get a dependency preserving decomposition. Okay, so so if it is sufficient to test only those dependencies on each individual relation of a decomposition in order to ensure that all FDs hold, then it is called dependency preserving. But it is not always possible to achieve both BCNF and dependency preservation. Okay, so because it is not always possible, there is a weaker normal form which is known as third normal form. So what we are saying is that if we have a BCNF decomposition, we really have good database design, and the amount of redundancy is much reduced. But in order to achieve a BCNF decomposition from a schema which is not in BCNF, we might end up in a situation where the decomposition is not dependency preserving. Remember that this dependency preserving is directly not related to the notion of lossless decomposition, where the lossless decomposition is a primary requirement, that we definitely would like to have a decomposition which is lossless, so that when we join them, we should get back the original tuples in the original relation. Okay, and this is different. This is about this decomposition. What we are talking about is always going to be lossless, as we'll very quickly see. But even if it is lossless, it is not necessary that the BCNF decomposition will result in such dependency preserving decomposition. So what is this third normal form? A relation schema R is in third normal form or 3NF if for all such alpha to beta in F plus at least one of the following holds. So now you see that here there are three such conditions, and if any one of them hold, that is sufficient to have a schema in 3NF. And of these, the first two are same as what we had for BCNF. That is, alpha to beta is trivial, and number two is alpha is a super key of R. And the third one, which is making it like this weaker form, is that if the third condition also is satisfied, then we say that the schema is in third normal form. So what is that? So each attribute A in beta minus alpha. So again, you see the notation A denotes an attribute, uppercase letter in beta minus alpha. That means the columns which are in beta and not in alpha. So each such attribute in beta minus alpha is contained in a candidate key of R. So what it means that there are candidate keys of R which we know what they mean. So any attribute which is not any attribute which is in beta minus alpha, they must be contained in some candidate key of R. And here what is very important is that each attribute must be contained in a candidate key of R and not necessarily in the same candidate key of R. So it means that each attribute may be in a different candidate key. So if a relation is in BCNF, of course it is in 3NF because the conditions for BCNF are tighter than those for 3NF. So, but the third condition is a minimal relaxation of BCNF to ensure dependency preservation. So, if we go for this third normal form, then what happens is that then always the decomposition is can be shown to be dependency preservation. We are not going to the proof of it, but if instead of a BCNF decomposition, we go for a 3NF decomposition for a schema which is not in BCNF, then what it means is that the decomposition that you will get that may not be in BCNF but in 3NF, but all such 3NF decompositions are guaranteed to be dependency preservations, meaning that all the FDs in F plus can be checked from any one of those decomposed schemas, and we do not need to join those schemas to be able to check all the FDs that are there in F plus. So that is the meaning of dependency preservation. So finally, if we try to sum what we have so far said, and we'll look into, of course, how this decomposition is done, is that our goal is that let R be a relation schema with a set F of functional dependencies. First of all, decide whether a relation schema R is a good form. That means if our target is BCNF, so we see that whether R is in BCNF or not. In case that the relation is not in BCNF, that is not in good form, we decompose it into a set of schema R1 to Rn such that each relation schema is in good form. The decomposition is, of course, a lossless joint decomposition. That is the basic requirement, and preferably the decomposition should be dependency preserving. So what it means is that if we do the decomposition of R into R1, R2, Rn and try to enforce that each of them is in BCNF, then it might so happen that for this particular schema and the given set of FDs, this decomposition is dependency preserving, but there is also a chance that some of the decomposition is not dependency preserving. And if we are okay with that, then it is fine. If we want to stick strictly to BCNF decomposition, even though the decomposition may not be dependency preserving, and we agree with that, we are fine. So, but we have to remember that whenever we do so, if we want to, not if we will definitely require to check for the FDs when tuples are inserted in those decomposed relations. We have to ensure that the FDs are satisfied. Otherwise, there is no point claiming that these are the valid FDs. Okay, so because those FDs are specified, we also have to ensure that when tuples are inserted in the decomposed schema, the FDs are not violated. And if we are okay to check for FDs through joins and we don't mind that, then we we can go for only BCNF decomposition. If for us the decomposition being in BCNF is more important, then we can go for it and be ready to do the joins at the time of checking for FDs. But if we are more particular about not requiring to do the join during enforcing of FDs, then if we try to stick to BCNF, we might end up in such dependency, not dependency preserving positions, and hence we might have planned for a 3NF decomposition. But of course, that if we go for 3NF, then each relation schema is in good form. So we have minimal relaxation, and we are okay with 3NF schemas that are in 3NF also, even though that might not be in BCNF. Now, beyond BCNF, there is another important term, so which we need to understand, and there are some schemas in BCNF that do not seem to be sufficiently normalized. So let us have this example. We have instructor info, ID, child name, and phone, where an instructor may have more than one phone and can have multiple children. So if we have this, so the instructor, this 99999, has these two phones, 512555124, and the other ending in 4321, as has two children, David and William. Now, if we keep this all together in one relation, then what we notice is that this phone, if we keep the phone along with the child name, then the same phone number we have to repeat for both the children. So I have 512555124 for David, and also with William, which is the first and the third tuple, and similarly the phone number 4321 with David and William, which are the second and the fourth tuple. Now, if we look at this, that if we only kept say 1234 with David and 4321 with William, uh, in that case, it would have apparently meant that this phone number 1234 is meant for the child David, and 4321 is meant for the child William, but which is not exactly correct, because these phone numbers are not specific to the children's name. So in that case, what we'll do is that we would have required to repeat this 4 times, and each phone number will be matched with each of the child name. But that, of course, we very well understand is is indeed having a lot of redundant data kept in this particular table. But the point that is important is that here, if you see that there are no non-trivial functional dependencies, so there is no, we are not saying there is any functional dependency like ID to child name, or ID to phone, or child name to ID, or child name to phone, or phone to ID, or phone to child name. So only functional dependency we have here is on the left hand side, alpha is ID child name phone, and on the right hand side, beta is also ID child name phone. So the only FD that we have is from ID child name phone to ID child name phone, but then it means alpha function determines beta, where beta is equal to alpha, so which satisfies that beta is a subset of alpha, including improper subset. Like if you see this trivially, beta is the first bullet, beta is a subset of alpha. So in this example, what we would have had is that the only FD that we have is a trivial functional dependency. So there are no non-trivial functional dependencies, and because the only functional dependency is a trivial functional dependency, then as per our definition of BCNF, that this alpha to beta is trivial, and that means that this schema is actually in BCNF form. But even though it is in BCNF form, we very well understand that it is not a great design, and it has got a lot of redundancy. Okay, so there could be insertion anomalies, as we have discussed before, because of the redundancy. If we add a phone number 919819992 whatever to 99999, then you see that we have to unnecessarily add these two tuples. If not, if we add only one child name, then it will appear that this phone number is associated with that particular child. So that means that this slide's title is "How good is BCNF?" So we understand that BCNF is good to have in certain contexts, but there are also indeed some other contexts where we need something beyond BCNF. Okay, and that is what we had mentioned here at the beginning, and we'll go to the discussion later, that this theory, as we said, is based on functional dependencies and multi-valued dependencies. So this BCNF that we are talking about, this is in the context of functional dependencies, and the reason why this particular schema is not good, that is not because of any issue with functional dependencies, but rather for multi-valued dependencies. And multi-valued dependency has some connotation with this multi-valued attributes we had seen before. So we'll see that for multi-valued dependency, what is the formal definition. So what of course we understand is that this particular schema, we would definitely need to decompose it into id and child name. Is one schema, inst child, the other is inst phone. But we can figure out that this is something which is even beyond BCNF, and this is often what is called fourth normal form. So we have so far talked about first normal form when we said that this would be atomic. The second normal form is not of much use, so we do not discuss about that. The third normal form we have defined. The BCNF we have also defined, and then we are talking about fourth normal form, which arises due to multi-valued dependency. So we'll look into this fourth normal form also later. Okay. Now, so now what it means is that we have talked about functional dependencies. We have defined what is BCNF in terms of trivial functional dependencies and super key and so on. And now what we'll do is that we'll now consider the formal theory that tells us which functional dependencies are implied logically by a given set of functional dependencies. So we are given that F, and then how we compute that F plus, that is what we need to see. And then we will develop algorithms to generate lossless decompositions into BCNF and 3NF, and also algorithms to test if a decomposition is dependency preserving. So we need these three things: that formal theory to get that F plus from F, of course, then how to generate a lossless decomposition into BCNF and 3NF, and then we also need to check if a decomposition that we have made is dependency preserving or not. So we will start this discussion about getting the closure of the set of functional dependencies, which is this first point here. So given a set F of functional dependencies, there are certain other FDs that are logically implied by F. As we have mentioned already, that if A to B and B to C are in F, then A to C is also implied, and hence A to C will be there in F plus, other than this A to B and B to C, which are already there in F. And the set of all functional dependencies logically implied by F is called the closure of F. And we, of course, denote the closure of F by F plus. So how do I get F plus from F? So here is this notion of Armstrong's axioms. So what we do is that for every such functional dependency in F, we define these through these axioms, that what all other FDs actually hold on the same schema R on which F is defined. So these Armstrong's axioms, there are three such axioms. What it says is that if beta is a subset of alpha, then alpha functionally determines beta, which is quite obvious. As we said, if id comma name functionally determines name, then we have name is a subset of alpha. So what it means is that then alpha will always functionally determine beta. So id name functionally determines beta. So here it is the first axiom that then alpha to beta is always going to hold. Okay. Second is that if alpha functionally determines beta, then if we augment the alpha, the set of columns in alpha, with another set of columns gamma, then this union of the columns in alpha and gamma, which is gamma alpha, that will functionally determine gamma beta, which is called the augmentation. And finally that we mentioned already here is that if alpha functionally determines beta and beta functionally determines gamma, then alpha functionally determines gamma, and this is what is called transitivity. So these are Armstrong's axioms or rules, that is reflexivity, augmentation, and transitivity. And these rules have been shown that they are sound. They generate only functional dependencies that actually hold, and they are complete means they generate all functional dependencies that hold. So we are not going to the proof of it, but we assume that these rules are sound and complete. So what does it all mean? It means that we are given f, we can, as the first bit says, that we can find f plus, the closure of f, by repeatedly applying Armstrong's axioms, and these are the three axioms. And if we apply them repeatedly till we end up in a situation where there is no further addition to the set f plus, then we have achieved the complete closure of f. And if we keep applying them, then because these are sound and complete, we will not get any incorrect uh, fd in f plus, and also we'll get all um, fds that are logically implied by those in f also in f plus. So simply, so if we put that the procedure for computing f plus, it is very straightforward to compute the closure of a set of functional dependencies f. So f is given to us and r is given to us, which is the schema, and then we initialize f plus equal to f, and then it is simply that we repeat for each functional dependency f in f plus, apply reflexivity and augmentation rules on f, add the resulting functional dependencies to f plus, and for each pair of functional dependencies f1 and f2 and f plus, if f1 can and f2 can be combined using transitivity, then add the resulting functional dependency to f plus until f plus does not change any further. So it is fairly simple that as we see that here we apply this reflexivity and augmentation. So these are, as you see, that reflexivity and augmentation are for one functional dependency alpha to beta, okay, and this the third one transitivity is for a pair of FDs alpha to beta and beta to gamma, and hence we say that for each pair of FDs f1 f2 in f plus, they can be combined using transitivity, then add that resulting functional dependency to f plus. So this is how we can compute the closure of a given set of functional dependencies f. So this is what is the starting point for functional dependency theory, that we determine how we can get the closure of the given set of functional dependencies. And why we are talking about it? Because you see that for BCNF we say that this we are given a schema R and a non sorry so we are a relation schema R is in BCNF with respect to a set F of functional dependencies. If for all functional dependencies in F plus of the form alpha to beta, either of these two conditions need to be satisfied. So that means that for doing anything with BCNF, we first have to get the closure F plus of the given set of functional dependencies F. Okay, and that is what we said here, that we start with the first step of how to get the f plus from f, and this is how we get it by uh, applying Armstrong's axioms of reflexivity, augmentation, and transitivity on the functional dependencies f that are there in f. But we, of course, as we keep growing f to f plus, so that's why f plus is initialized to f, and now as we keep adding more and more functional dependencies in f plus, so we have to now do the same thing, that first we get maybe first set of new functional dependencies from f into f plus, and then those which are there in f plus will again be used to get more functional dependencies by applying the axioms, and then for each pair we'll be taking for transitivity, and we will repeat it because of transitivity. Now we'll get some more FDs, and again for those we have to check for reflexivity and augmentation and so on. So we do that, and till we get to a convergence, and that is what is the process of getting F plus. But we'll see later some alternative procedure for doing this task. So uh, what we also have is that we'll also have some additional rules. But I think instead of going into that, which might make things a little confusing if taken together, so instead of that, I'll stop here. And tomorrow I'll take a look at some of the other rules and then actual examples of computing f plus from f. So that I will take up in the tomorrow's class. So we'll stop at this because we have got some good idea now about what is this BCNF all about, why we would need BCNF through the examples we have seen that otherwise we can have these types of schemas which are not in BCNF and which actually resulted in the redundancy which in turn would have resulted in inconsistencies. So with that idea, we know that we have to go for some formal definition of a good design, which we have said BCNF is a good design. If it is not in BCNF, we'll decompose it and try to get BCNF schemas. And as I said, suppose I decompose R into R1 and R2, what can happen is R2 is in BCNF already, but R1 is not in BCNF. And suppose I want to go for only BCNF, even though it might not be dependency preserving, then from R as we go at R1 and R2, and R is in BCNF, sorry, R2 is in BCNF, then R1 I have to decompose into R11 and R12, where again R11 might be in BCNF, but R12 is not, then R12 I have to decompose into R121 and R122. And now if both R121 and R122 are in BCNF, then my entire decomposition will be that R11, R121, R122, and uh, R2. So that is how we finally end up getting those leaf level decomposed schemas. That forms my final schema. So as we say that R is decomposed into a number of such schemas, okay, and that is when we'll get the final set of schemas which we'll have in our database, which are all in BCNF. Of course, assuming that we are trying to go for PCNF. If we are okay with 3NF, then we'll decompose it so that we get 3NF schemas, and we'll stop at that if it is already in 3NF. So, so again, to remember that if I decompose R into R1, R2, and then R1 further in R11 and R12 and R12 in R121 and R22, then R11, R121, R122, and R2, this will be my final set of schema. So the intermediate ones, of course, will not be there in the database. Okay. So that is what we need to do, and we'll see some examples in our tomorrow's class. So I'll stop here. Is there any questions on this?